Hello, students. Today we want to talk about one-to-one functions and the companion object, which is called the inverse function. What we're going to realize is that one-to-one functions are a special type of function that can be inverted. That is, if we think of a function as a forward path, then we can also think of a reverse path if the function is one-to-one. Now, why would you think we'd be studying this? Well, paths or functions in mathematics, especially STEM, are very important. And the calculus of functions and invertible functions is very important and critical to the study of STEM disciplines. And another thing, too, we want to set the groundwork for two very important functions, which are inverses. They are the base A exponential and the base A logarithm. So with the information that we're able to generate about one-to-one functions and invertible functions, we can transfer all of that to these new functions. So let me share my screen. Now, as I've said, the topic at present will be one-to-one functions and inverse functions. Now, the definition of one-to-one function will remind you a little bit of the definition of a function. When we define a function, we know that every input has exactly one output. And that's very useful. When you think about plotting points on a function, none of them will never align on a vertical line. That is, if you have an input, there's exactly one output. Now, when we discuss one-to-one function, we start with a function, but we have a more restrictive identification. That is, if we have two elements that are equal in the range, it must be the case that their inputs are equal. That is, every range element is only mapped into one element from the domain. That is, if you look at this particular example here, notice the way I've constructed this is that all of the range elements are unique in the sense that they exist one time and one time only. That is, 1 is mapped into 2, 2 is mapped into 3, -1 is mapped into 4, and 7 is mapped into 0. One-to-one functions do not repeat range elements. So an example of a one-to-one function that you have studied previously would be an increasing function. That is, the outputs become larger and larger as you put in different inputs, but they never repeat. That's an excellent example of a one-to-one function. Decreasing functions also share that. Functions that are not one-to-one, we are very aware of. For instance, quadratic functions. F of x equal x squared is not one-to-one because, of course, if we substitute 2 and -2 from the domain, we get the same output of 4. So if we can determine that a function is one-to-one, then we can define a reverse path. Now, just as I've said before, function g is one-to-one. That is, there is no ordered pair that has the same range element. Now, of course, you know you could have a constant function and all the range elements are the same. It's still a function, but it's clearly not one-to-one. So what I've said here is that one-to-one functions are invertible. One notation that we use, as I've noted here for the reverse path or the inverse function, is the function letter with the superscript -1. So for instance, for the inverse of g, we could simply write the ordered pairs in reverse order. That is 2, 1, 3, 2, 4, comma, -1, and 0, comma, 7. And that would be what we would call a reverse path. So again, let me write that, reverse path. Now, one thing that's important here is in order to get that reverse path, what is going on is exactly what you think. That is, the domain of f becomes the range of the inverse function. The range of f becomes the domain of the inverse function. So if we were to think of plotting these ordered pairs, considering the independent variable to be x, let's go ahead and plot some of these. We're going to get a nice symmetry property. So again, one thing we're tacitly assuming is that the independent variable in each case is x, and I'll say more about that later. But let's just go ahead and plot these. I'm going to plot the original function in blue, so we have 1, 2. Let me go ahead and mark off these in the same color. One, let's see, we've got the largest we need is a 7, 3, 4, 5, 6, 7. Just get a nice, neat graph, and then we're going to need a -1. And then let's see, we've got, let's just see what we have here, 2, 3, 4, 0. Go ahead and mark everything off. Again, this is not Rembrandt, as I always often say, but it will do the trick. So we have 1, 2. We have 2, 3. We have -1, 4. So -1, 4. And we have 7, 0. 1, 2, 3, 4, 5, 6, 7 right here, an intercept. Now I will plot the inverse function here with red. So we'll have 2, 1. We'll have 3, 2. We'll have 4, -1. So 1, 2, 3, 4, and a -1. And then we have 0, 7. So let me mark this off here. 4, 5, 6, 7. Now, one thing that's interesting about this, and let me do this a little differently so you can actually see the color there. There we go. That looks a little better. We get a reflective property here. So I'm going to go ahead and draw in the line y = x. So I'll just take, we've got the 0, 0, and then 2, 2. The interesting thing about the function and the inverse is that we get a reflection in the line y = x, because all we've done is reverse the x and y coordinates. So when you think of the point here, the red point and the blue point, we could just do a connection line where these two distances are equal. That is, we see that the line y = x becomes a mirror. That is, the function g and its inverse are reflections in the line y = x. Notice here we've got some simpler ones. Let me just move the page so I can go ahead and draw these. just dot here. We get these little connection lines that basically mirror the red points to give us the blue points and vice versa. That's certainly not by happenstance. That is, we don't just get lucky. Just by simply reversing the X and the Y coordinates, we are basically reflecting all of the points in the line Y equal X. That is a very simple geometric construction. Now, this is a very, very simple function. It has 4 elements. G is 1-to-1, so we can write a reverse path. But I just want to write this. The graphs of G and G inverse are reflections in the line Y equals X. And what we see is that the domain of the inverse function, which is the new function, is actually the range of the original function G, because that's the reverse path. You move from the domain of G into the range of G, and then you can go in reverse by moving from the range of G into the domain of G. So therefore, the range of G inverse is just the domain of G. So there's really nothing new. One-to-one functions implicitly define a reverse path. That is, when you're in the range, the target in the domain is one element. Because the function is 1-to-1, the path back to the domain is unique. If the function were not 1-to-1, you would not have the unique path. And that's why we don't define the inverse function. So this is something that is unambiguous. So when you start with a 1-to-1 function, you necessarily have a reverse path. Every function will be onto its range. And when we want to return, we have to know that that path is well defined. And that will always happen with the 1-to-1 function. Now, this is a very, very simple example, but the illustration is excellent because it gives you the reflective property very simply. So again, notice here, 1, 2, -1, 7. That is the domain of G. But now what we see is that when we write the domain 1, 2, -1, 7 of G, it becomes the range of the inverse function. When we write the range of G, that becomes the domain of the inverse function. So the key here is if we're simply operating with finite functions like G, it's very simple to check 1-to-1. We just look at the coordinates and make sure that the second coordinate has not repeated amongst any of the ordered pairs. That is a finite situation, or in some cases, we could have a countably infinite situation, but we'll save that for calculus. So checking this in a finite case is very simple. What we would like to do, because you know in this class, we spend many of our examples studying functions that have infinite domains and infinite ranges. That is, when we compute the domain, it's a subset of the real numbers that is infinite. We can't just count the numbers. There are too many to count. The range is likewise. So we want to be able to take this idea and be able to write a reverse path in terms of a formula. Now, the process here we're going to say more about, that is using the line y equal x as a mirror to actually draw the inverse function if we have a sketch of the beginning function, so to speak. Now, you might be thinking, we talk about inverse and then we say the beginning function. Notice g is also invertible. I mean, we could say that g is the inverse of g to the -1. We can also say that, but we think of a beginning function, so to speak. We think of a function with which we start, show it's 1-to-1, and then we write the inverse. So again, it doesn't matter which function you start with, they're both inverses of each other. It's just that as we work in practice and as you work your examples in your STEM class, we will have a function with which we begin, show 1-to-1, and then what do? We compute the reverse path or the inverse function. Notice here, as I've said before, the inverse function was very easy to write. We just simply reverse the order of the x and y coordinates to get the reverse path. Now, before we do this example here, I want to make one more comment about the inverse functions and what properties they have. I'm going to go ahead and write the functions again. Let's just start out. So I've got a little bit more room here. So we've got 1, 2. We have 2, 3. We have -1, 4. It's always good to start out with a finite case because you can see so much of the detail without the clutter of a lot of additional work. And now just flip them around. 2, 1, 3, 2, 4, -1, and 0, 7. Just like we wrote on the previous page here. I'm just simply repeating what I've done here. Okay? Now, one thing that you might be thinking about is that if we have the forward path from the domain of G to the range of G and the reverse path from the range of G back to the domain of G, we basically end up, so to speak, where we began. That is, if you think of composing the forward path and the reverse path, you should get an identity function. Let me show you what I'm talking about. So this is what we call inverse rules. Inverse rules. So we could say G composed with G inverse of X, again, writing all of the independent variables in terms of X for simplicity. We don't always do this, but for the very simple example here, we're always going to assume that the independent variable is X just for the sake of writing these. So this would be G of G inverse of X. So this should be X. And we would say for X in the domain of the inverse function, which is actually the range of G, right? And then the second one would be reversing the order. That is, we would say G inverse of G of X would be G inverse of G of X, which should also be X when X is in the domain of G. So the key here is that it doesn't matter which order you go. If you start in the domain of G and map via G into its range, oh, I've got too many parentheses here. Let me get rid of that. And map into the range, you're basically doing what we do here. That is, we're starting in the domain of G and we're mapping to the range. And then, of course, the reverse path, the way we've defined G inverse, will take you right back to where you started. So again, what's important here is that if we start here, as we have with this, we map into the domain and then back to the range of G. For this one, we start here, we map here, and then back to where we started. So it doesn't matter about the order, because we know in general, when we compose two functions, the order does make a difference. But this is that special exception that I mentioned in the previous lecture. That is, when you have one-to-one functions, the reverse and forward paths create the identity function under composition. That is, where you begin is where you end. So let's just take a couple of examples here and prove this. Let's start with G of 1 and apply the inverse. So we'll say, here's an example just to show you what I'm talking about in the finite case. Say we have G inverse composed with G, and we'll just take an element in the domain of G, and so we'll have 1. So we have G inverse of G of 1. Well, G of 1 is 2. So we have, or I left off the -1, so we have G minus 1 of 2. And then, of course, we go to the, what does G inverse do to 2? Well, we find the 2, it maps it into 1. So what we see is input equals the output. This is not a surprise. I mean, of course, we know this is going to happen, but mechanically, it should happen also. Let's flip things around. Let's do another example. So we start with G, the domain of G inverse, which is the range of G. So we have G composed with G inverse. And let's just take some element in the domain of G. Let's just do 4 from the G inverse. So we have 4. So we have G of G inverse of 4. Well, what does G inverse do to 4? It takes it into -1. So this is G of -1. And then we go up here and see, what does G do to -1? Well, it takes it right into 4. So again, what we see is input equals output. Input equals output. And it doesn't matter what order. The inverse function and its original function are both one-to-one. So we get this incredible composition rule. But what's important, very important, is that they have to make sense, right? So when we do this composition, we're starting with X in the domain of G inverse. So we must be sure that that is applied. When we do in the other order, we're starting with X in the domain of G. So this simple example provides a very nice landscape for discussing a one-to-one function. One-to-one functions are very, very important because the one-to-one function defines a reverse path. And so if we have an example where we have infinitely many numbers in the domain and range, how do we do the same that we've done here? Well, there's really no difference. It just usually means that we have a little bit more algebra to do, but we abide by the same rules and the same definition. So let's look at another example, which is going back to where we started with the previous example page. So if you remember from the first page, let me show you that. We had this example. That is, f of x equal x squared minus 2, where x is greater than or equal to 0 is 1-to-1. Notice the domain is restricted. It's a quadratic function with a restricted domain. So let me write that down. So we have f of x equals x squared minus 2, where x is greater than or equal to 0. So here the domain is provided to us. We're not simply taking the largest possible domain. We have a domain that provides the one-to-oneness, so to speak. So here we can say the domain of f is 0 to infinity. That is all x that are equal to 0 and greater. And then, of course, if the values of x are 0 and greater, that means the minimum of f is simply -2. And then, of course, the values will grow after that. So what you can see here is that this will provide an increasing function, as one of the examples I mentioned earlier about being one-to-one. So let's go ahead and write that down. The range of f will just be -2 to infinity. Again, be sure to use the bracket so you can note that those numbers are included. Now, of course, what's important here, let me just get a little focus here. What's important here is that we should be able to do the switch, that is, think about the reverse path. But before we do that, we want to specify that we indeed have a one-to-one function. So what we can do is use the definition. Notice it's very critical that we have x greater than or equal to 0. So what we're going to do is suppose that f of a equals f of b. That is, we have two elements in the range that are equal. Now note, we have the same restriction. A is in the domain, so it's greater than or equal to 0, and B is in the domain of f, so it must be greater than or equal to 0. So now we just fill in the formula where we replace x with A and x with B. So we have a squared minus 2 equals b squared minus 2. Well, this is very simple, and you're thinking this won't be very difficult to do. Notice the negatives, the -2's absorb. They're gone. And so we end up with a squared equals b squared. Now, at this point, we can apply factorization, or we can just use the square root principle. That is, if we have a squared equals b squared. So by the square root property, we have a equals plus or minus the square root of b squared. Now, of course, the square root of b squared is what? The absolute value of b by definition. So we have a equals plus or minus the absolute value of b. Now, of course, a is greater than or equal to 0, so we would not select, in this case, the negative radical, because we know the absolute value of b is greater than or equal to 0 by definition. So this would imply that we select the positive absolute value. So therefore, this implies that a equals the absolute value of b. Again, this is done because a is greater than or equal to 0 by definition. And now, of course, we use the same restraint on b. If b is greater than or equal to 0, by definition, its absolute value is just b. So this equals b because b itself is greater than or equal to 0. So now what we see is we get the result that we were looking for. That is, if f of a equals f of b, this implies that a equals b. That is, it must be the case that the inputs were equal. So by definition, f is 1-to-1. Now, of course, there are mechanisms that that would say, okay, well, we could apply what we call a horizontal line test. Well, that only works if you're actually starting with, a picture of a function, and that's fine. But when we actually start with a version of the function, just like in the finite case, or in this case, in terms of a formula, you can't draw the function unless you understand it. So that's really not the best way to think about it. It's certainly fine if you have a picture of a function that's given to you, and you could say, well, that function appears to be one-to-one, but that's certainly not a way you would actually show this function is one-to-one. That makes no sense, because drawings are simply a reasonable facsimile of what we think the function is, but we only can do that when we understand many important characteristics of the function. So now, just like with the very simple case we started with, remember, the function with 4 elements turned out to be one-to-one because we saw that the range elements never repeated. So we definitely had a reverse path, easy reverse path. Now, in the infinite case, we have also a reverse path, and I'll show you how you can do that. So we'll just say that this implies that f does define an inverse function. That is, f inverse exists. And it's important to remember at this point that these restrictions are important. So if we want to think of the notation y equal f of x, we can already say that x, again, right here, lives here, 0 to infinity. And if we're replacing f with y, we say y lives from -2 to infinity. And that keeps the, so to speak, what do we call, what I'm looking for? The universe of x is here. The universe of y is here. So we know where they live, so to speak. And we want to make sure we keep that focused in our brains as we compute a formula for the inverse function. So it's better to think of it this way, and then we can make correct deductions as we work to find a formula. So here's how we do it. I'll just start with this. We just say y equals x squared minus 2. Now, at this point, we're not going to interchange anything. That tends to be the way that many books will tell you to do, but it confuses where x and y live. So do not do that. So this is number 1, to just simply set the function equal to y. And secondly, we want to solve for x. So when we solve for x, we just want to isolate x squared. So we'll just do an interchange. So we have x squared equals y plus 2. That is, isolate the x squared. So let me just write here, solve for x. Now, many times, as you'll find in the calculus, you may have a function that is one-to-one, but the explicit solution for x in terms of y may not be possible. That does not mean that the inverse function doesn't exist. But for now, we will either have a nice symbol for the inverse function, or we will be able to do the algebra. So when we get to the base A logarithm and the base A exponential, that will be a symbolic case of how we will write an inverse function, just because we know the existence of it, but we don't have a mechanical way in terms of algebra to write it unless we just symbolize it. So at this point, we're back to what we were up here. So it's good that we did the one-to-one here. So now we'll apply the square root property. So we have x is equal to plus or minus the square root of y plus 2. Now, again, there are many ways that you can always affect the one-to-one and solving for the inverse function. It doesn't necessarily mean that the technique is unique, but as long as you use good deductions, you will not have a problem as you work through the execution of the steps. Now, of course, we go back up here and we see that x is non-negative, 0 to infinity. So again, just like we did here, we will select the positive radical. So select plus as x is greater than or equal to 0. So we need that piece of information here to make this deduction. So this will imply that x equals the principal square root of y plus 2. Now, this is a reverse path, but it's not stated the way we actually stated it on the first page of our lecture. That is, we will prefer that the inverse function be notated with the same independent variable. So once we have isolated x, that is, we've solved for x in terms of y, we can now do the interchange. So if you want, you could think of this as the inverse function in terms of y, that is the reverse path. But in order to get the reflective property, that is in the line y equal x, we need all of our functions to have the same independent variable. So now we define, in this case, f inverse of x. Again, we interchange now in our formula to be the square root of x plus 2. So if you like, you can think of this as just f inverse of y as a reverse path, where you don't do an interchange. And then, of course, the graph of the inverse is really looking at the graph of f, but again, you're now living on the independent axis, which is now y, and you're staring at it differently. So again, just remember the one-to-one function implicitly defines the reverse path, but we like to distinguish our functions and have them basically exhibit the reflective property. And when we have them as separate functions, that reflective property is very nice mathematically. Okay, so we distinguish the inverse function by assigning the same independent variable. So now we look at this and say, okay, we're good here. So notice here. Here is the domain of f. This is the range of f, but you now see that this set is now the domain of the inverse function, which is exactly what it would be if you computed the domain of this function. So all of this must be consistent with what you would get if you just started with this function. Okay, so if you computed the domain of this function as just an exercise, you would see that this set would be the domain. So now we have exactly what we thought we would have. So notice here, we'll just write it down. Domain of f inverse is actually the range of f, which is -2 to infinity. And of course, the range of f inverse is just the domain of the original function, which is 0 to infinity. Okay, so when you have a formula with domains that are infinite, ranges that are infinite, then you apply the same techniques, but there's much more algebra to do. Again, the finite case is an excellent example to start with. It's very easy to write the reverse path by just simply interchanging the x and y, and then treating the interchange order pair with the same x-y order that you would for the beginning function. And so in order to do that here, We solve for x in terms of y, and then we interchange. And that provides the reflective property that we're looking for. So now let's just go ahead and do the graph with that. We've got all the information. So one thing that you can find that's very useful as a technique to display your work. I mean, once you have the inverse functions, you don't have to do this, but it is kind of interesting when you think about it. So now let's go ahead and draw our XY axes. Just give a lot of space here. Now, the original function, we have f of x equals x squared minus 2. And then the inverse function, we computed to be the square root of x plus 2. So what we can do is just use some really simple points here. And again, nothing very difficult. So first, when we have f, we can just also write here, let's just go ahead and say x element 0 to infinity. So let's just write down several points here. So for instance, we'll start with 0. So we'll get a what? 0, -2. And then if you like, you could put in, let's keep it really simple here. Let's put in a 4. Well, actually a 2. Let's keep it 2 squared is 4. Let's put in 2, keep it really simple. So if we put in the 2, we get 4. 4 minus 2 is 2. And then if you want an additional point, just simple, let's just take a 3. We'll keep them close together. So we'll have, in this case, we'll put in 3, and that will be 9 minus 2, which is a 7. So let's go ahead and get the tick marks so that it'll be represented well. So we've got like a 1 and a 2, and we've got 1, 2, 3, 4, 5, 6, 7. Of course, this is not Rembrandt, just a reasonable facsimile, and 2 and 2. And then, so these are the values or the ordered pairs for F. And then, of course, for F inverse, we can just flip them around. So we get -2, 0. Well, 2, 2, that's on the reflective line, and 3, 7. So now let's go ahead and plot both of these, and I'll put this in a blue box. You don't have to write these out, but it just kind of reinforces the idea of the reflective property. So now we have a 0, -2. I'll go ahead and do these, do the first function in red. So 0, -2, and then 2, 2. And then we've got 3, 7. So let me get another mark here, 3, and then 7 up here. So we'll go ahead and connect that. Again, we're not drawing it infinitely, but we're just trying to get a little curvature there. That's actually the vertex of a quadratic function. So this is what we call F. And let us go ahead and draw the ordered pairs for the inverse. So we have -2, 0. So let's go ahead and put some more tick marks here. So again, just the reflection of that one that we see here. And then 2, 2, again, that's on the reflective line. And then 3, 7. Oh, well, yeah. Let me flip those around. That'd be useful. One good thing about the math, it certainly lets you know when you put things in the wrong order. So let's get some more tick marks here. So we got 1, 2, 3, 4, 5, 6, 7. So we have 7, 3. So let's see, 7 about right there. So we'll go ahead and connect these. Get a little bit of curvature there. So here's F inverse. Now, of course, notice what I've done here. I haven't extended these infinitely. All we're doing is just utilizing the fact that we know the shape of the quadratic function, just like we did with transformations. And then we can just use some simple points. And so now, of course, if we did our little reflective line, y equal x, we see that we have this nice symmetry. And of course, the perfection is not the essence here, just showing the fact that if you assign the same independent variable to the inverse map or the reverse path, then you get this reflective property, which is very, very useful. Again, remember, we can often say, if we have a point alpha beta, for instance, we could say alpha beta using this scheme that we've set up is an element of F if and only if beta alpha is an element of F inverse. That is, if we're always treating the independent variable as the same, just like when we were doing the finite case. Because remember, when we look at this function here, if we are to think of being on the independent axis as y, then we can look at this function as starting with independent variable y and then moving into dependent variable x. That is when we actually solve for x as a function of y. So in order to utilize the distinction of a separate map with same independent variable, we do this mechanism here. Okay, just remember that the one-to-one function implicitly defines a reverse path, and we enjoy the operation of utilizing the same independent variable to, again, distinguish the reverse path as its own separate function. And then, of course, we get this really, really unique reflective property, which is just a very simple geometric result that is not overly difficult at all. It's just when we flip the coordinates of a pair, we are basically reflecting that point in the line y equal x, which again is just a simple geometric manifestation of the Cartesian coordinate system. So again, just remember, when we think about inverse functions and we think about one-to-one functions, the path is made for us. We simply have to follow the routine of solving for one variable in terms of another, or just in a finite case, just interchanging the ordered pairs, and we're done. Now, one thing that's interesting here is it's often very simple to write a inverse mechanism, but let's look at another example where we can utilize what we talked about with rational functions and see how the inverse map compares to the original map. So let's look at another example. We have f of x equals x divided by 2x plus 1. So that's our original function here. Now, one thing, again, like I said before, you can always use the reflective property to sketch the inverse or reverse path, to sketch the inverse function or the reverse path. Again, you're not trying to make a work of art, but you do want to think as I've done here. by taking some really simple points and just reversing them. And then you can get a reasonable graph if you have a good idea of what the original function looks like, using properties of functions that you know well from your work with transformations. So what we want to do here is first prove f is 1-to-1. And then, number 2, compute the inverse function. So what's important about all of this is just applying the same simple rules that we've already set up for this. They'll never change. Now, again, before we get started, let's just go ahead and factor f. So we have x, we've got what? 2 times x plus 1/2. So when we look at this, we can see that there is a 0 in the denominator. That's not a 0 upstairs. That is -1/2. So here, this implies that the domain of f will be all real numbers except -1/2. And we see that that defines a vertical asymptote. So we have vertical asymptote x equals -1/2. So that's just kind of a freebie there. And then, of course, we see the degree of the denominator and numerator are both 1. So we take the ratio of leading coefficients to get the horizontal asymptote. Horizontal asymptote is just y equals 1/2. That is, we have the 1 and the 2, so we get the horizontal line y equals 1/2. Now, just as some very simple ideas here, notice we have f of 0 is just 0. And again, when is f 0? When x is 0. So the y and the x-intercepts are the same. So we'll just say x-intercept, y-intercept, they're the same, just 0. So when we look at this, we've got some fairly simple ideas that are going on here. And we're thinking if we did our little sign test, again, we had the intercept of 0, the x-intercept, and then we have the -1/2. We'll spread this out so it's easy to see. So now, of course, if we just took some huge number bigger than 0, like 500, that's clearly positive. And then, of course, the x is to multiplicity 1, so we get something like this. We cross. And then, of course, at the -1/2, we don't cross, but the sign does change. So we've got plus, which is above. We have minus here, which is below. And then here we have plus, which is above. So that just gives us an idea of what the original graph looks like. It doesn't prove that it's 1-to-1, but it certainly gives us information that will be very helpful when we draw the function. Now, one thing that's important when we have the interchange of x and y, the vertical asymptotes become horizontal and the horizontal become vertical. And then, of course, the intercept doesn't really change. So that's just 0, 0. So now let's go ahead and do our proof. So f of A equals f of B. That is, we just start with A and B in this set here, avoiding -1/2. So we get A over 2A plus 1 equals B over 2B plus 1. Very simple algebra. Now, of course, what we can do here is just cross multiply. That's easily done here. So we have A times 2B plus 1 equals B times 2A plus 1. So now let's go ahead and multiply. So we have 2AB plus A equals 2AB plus B. Now, of course, the two ABs absorb, so those are gone. And then we're just left with A equals B. So that was quick. The quadratic example took a lot more work, much more complicated. Now, of course, I've got the domain here, but notice with this horizontal asymptote, we can actually write the range too. So I'll go ahead and write the range of f. Now we're tacitly assuming that the function never equals 1/2, and we could prove that. But for right now, this will just say that the range is negative infinity to 1/2 union 1/2 to infinity. So we exclude the horizontal asymptote, which is the case because we don't have any quadratics here, so we can't really double back. And the main thing about this is that since this is 1-to-1, it really does preclude that. So here, by definition, f is 1-to-1. So 1-to-1 functions are invertible. So this implies the reverse path, or f inverse, exists. Okay, so it's very simple when you think about it. When we use the definition here, f of A equals f of B, that is simply saying that if we have elements in the range that are equal, and we can show that A equals B, then those elements are actually unique. There's only one mapping from the domain. That is one map, the function maps only one element into that range element. And that's why we can define very unambiguously the reverse path. So that's really important when it comes to 1-to-1 functions. It's like maybe even and odd functions. It's very restrictive, but the payoff is useful if we can determine that the inverse function does exist. So now let's go ahead and compute it. We've done all the work to show 1-to-1, and we've done a lot of extra stuff that we did when we were graphing rational functions. So we'll make use of it. So now we have y equals, and the function is x divided by 2x plus 1. So this is the first step. We just set the function equal to y, and we solve for x. So we can cross multiply. So we have y times 2x plus 1 equals x. So this will give us a 2xy plus y equals x. Now, of course, we want to solve for x, so we want to get all the x's on one side and the non-x's on the other. So this will give us a 2xy minus x equals negative y. So take the x over and the y over, and that will give us what we need. So now we can factor the x. So we have x times 2y minus 1 equals negative y. And now, of course, we're assuming that this is well defined. Again, we see this, and I'll say more about it. If and only if x equals negative y divided by 2y minus 1. Now, if you like, it doesn't matter. Maybe you don't like all these negative signs, so you can multiply by -1 upstairs and downstairs just to get rid of some of them. Your choice. If you don't, it doesn't make it wrong. So this gives us a y divided by 1 minus 2y. So now we've solved for x in terms of y. So we define f inverse of x, now setting the independent variable the same to be x divided by 1 minus 2x. And now if we go back over here, you can see that the range of f does not include 1/2, which is the domain of f inverse, which has to be the case. This cannot include 1/2. And now when we think about it, as we move for this, looking at the horizontal asymptote, we see that negative 1/2 would not be hit in the range of f inverse, which is actually the domain of f, which we see we have here. So the consistency between the two functions is evident. You can always check that. Just remember, the domain of f in this particular case is the range of f inverse. The range of f is the domain of f inverse. They just simply interchange. So when we think about the reflective property, we're simply trying to magnify the existence of the reverse path and then utilize that distinction as a separate function by, again, assigning the same independent variable. Okay, so now we can simply write this and we are good. So there's our inverse function. And now in this particular case, this is from your lecture notes, this is number 5. Now, just as some extra, let's just go ahead and plot our f and then see if we can now write the inverse function. Here, let me, little less curvature. There we go. We'll spread this out a little bit so you can see it. The numbers are kind of bunched together. So now, if we look at the original function, we have a vertical asymptote of x equal negative 1/2 and a horizontal asymptote of y equal 1/2. So we'll spread this out a little bit. So we'll just say we've got a negative 1, 1, and then we'll do 1 and negative 1, just to make it a little bit larger here. So here's our negative 1, here's our 1, 1, negative 1. So we'll do our negative 1/2. So x equals negative 1/2. And then we have our y equal 1/2, just like you were doing with the rational function graphs. Very simple. Now we can use all of that information with our inverses. And of course, if you did the compositions, you get the identity like we did with the finite function. Those are good exercises, not very difficult. You know it's going to be the case, but just a good algebra practice. So now notice there's only one place where we get the negative, and that's in this area here. Otherwise, we're above the x-axis. So we'll go ahead and do this in blue. So let's go ahead and draw this part. Notice here, and this is actually quite important here. When we think about this part here, this is above. We have no driveways here. The only driveway is the 0 here. So we can go ahead and put this in. We have our approach the 1/2, and then just move right up here to infinity. There we go. And then on this side, we have the x-intercept, But of course, this is the region where the graph is below the x-axis, so we're going to hug the asymptote. Just run right up to here, and then hug the horizontal asymptote. Just like that. So there's F. This is F. And now we don't have to work very hard to get the inverse function. Even the reflective property is not going to be difficult. What's going to happen is that now the vertical asymptote x equal -1/2 becomes horizontal y equal -1/2. So we can go ahead and plot that. So we have y equals -1/2. And then we have the horizontal asymptote y equal 1/2 becomes a vertical asymptote x equal 1/2. So we'll go ahead and put that in. So now if we think about, again, we've got to cross and notice what's important about this and what makes this really simple. We'll do this in red. We've got the asymptote here, so we can use the reflective property to get this part. This piece is reflected down here. So we'll do that first since it's easiest. So we get that here. And now when we do the other reflection, again, we've got to be reflecting in the line y equal x. And so we've got to hug this line, but then we've got to cross through here and then hug this line. So we've got again, the horizontal asymptote, which is reflecting this part here, and then we have to reflect this part here. So again, very simple. There we go. So here's F inverse. So we still go through the same point here, still have the same point here, but now the graphs are easily done just using reflection. So we see reflection, the red reflecting the blue here, and then of course the red reflecting the blue here. So you can use the reflective property to get a fairly inexpensive graph without having to start over. I mean, if we look here, we could do the same sign test if you like. Notice if this were just the beginning setup, so do the following. So we have x, and we'll just have a -2x plus a 1. So you can factor the -2. So we have x -2 x minus a 1/2. So again, that's no surprise. That means that we have defined a vertical asymptote x equal 1/2, but we didn't have to do that because we already knew from the interchange. But again, you need to see that it actually turns out to be the same. And of course, we got the same intercept, so you can do that. So you have the 0 and you have the 1/2. Now, of course, if you take, a number over here like 500, of course, these two factors are positive, but the negative ensues here. So you get something like this below, and then of course we don't really cross, but we change sign, and then we have to run back here. So we have below, which we don't have to do, but you need to be convinced that this property or this technique actually works. Multiplicities are so important here. So now you can see from -∞ to 0 in this particular case. And I'll just say this, it's kind of important when you think about it. For instance, say you looked at this particular situation here. Notice if we take like negative 5,000. So that's negative, that's negative, that's negative. So we have negative. Notice this is important. We're right below the x-axis here. So notice as we move up to 0, we're below the x-axis. And then from this little piece right here, 0 to 1/2, we're above. Again, we don't have to do this sign test, but you need to see that by just using the reflective property, you can avoid that. And then, of course, for 1/2 to infinity, we're below. So the beauty of the one-to-one function and the inverse is that we can simply reverse everything. That is, the vertical asymptote x equal negative 1/2 becomes the horizontal asymptote y equal negative 1/2, as we see here. The horizontal asymptote y equal 1/2 becomes the vertical asymptote x equal 1/2, as we see here. So you don't have to start over. And what's interesting about the one-to-one functions is that they are so rich in the calculus. And you spend quite a bit of time understanding the calculus of invertible functions. And we see that as we continue on in the sequence of calculus and into other disciplines in mathematics and STEM, that the reverse path is extremely important. We have function theorems called the inverse function theorem and the implicit function theorem, which are just cornerstones of real analysis. So I hope that our study of the one-to-one and inverse function has been fruitful. Just remember, we use everything you've been working with at this point, and we define the one-to-one function, and then we take that one-to-one function and figure out what the reverse path is. So practice this, and just know that this will be something that you're going to see over and over as you continue in STEM. We'll see you later.